And then we go to the next speaker, who is Joe Paat. So please, Joe,
See.
the floor is yours.
Thank you. So can you hear me? Can everyone hear me?
I can hear you at least.
Okay, great. So thanks for the introduction and very nice talk, Daveen. So this project that I'll be speaking about today is joint work with Miriam Schluter, who's a postdoc in Zurich, and Emily Speakman, who's an assistant professor in Denver. And as the title suggests, in this project, what we do is we try to build lattice-free polyhedra. Okay, if you're not familiar with what these are, it's okay, I'll try to explain them in the next few slides. But if you have any questions on what I'm writing or what I've written down, please let me know. And to my knowledge, there's not much work done on actually building these sets. So if you have sort of conceptual questions, it's probably an open question. But anyway, so what is a lattice-free polyhedron? Well, for us, let me move this around. For us, we take a polyhedron P, and we say it's lattice-free if its interior has no lattice points inside. So a few things. For us, a lattice is really a mixed integer lattice. So it's Zn cross Rd. And we define the interior in sort of a special way, and this is done to unify our results. So for us, we define the interior of a polyhedron to be all of those points that strictly satisfy all of your inequalities. Okay. So this matches up with our intuition for interior, except in this very special case where we have this inequality 0x is less than or equal to 0. Sort of this, if you happen to have this inequality in your system, then we also consider this to be lattice-free. Okay, this is kind of a technical thing, but I'll comment more on this later. For the time being, we can really think of lattice-free sets as sort of what our intuition has led to so far, that there's no lattice points in the interior. Okay, so this is lattice-free, and this polyhedron on the right is not lattice-free. So there's been a lot of work done on lattice-free sets and how they generate cutting points. And Daveen actually had a very nice list of references in his talk, and I'm sure I've missed many, many people. But here are just a handful of people who have worked on this question in the last 10 years or so. And in this talk, we change gears and we actually consider how lattice-free sets can be used to certify optimality for convex integer programs. Okay, and the list of authors who have worked on this is much shorter, at least to my knowledge, it's much shorter. Okay, so our goal is to use lattice-free sets to certify optimality for convex problems. And for us, so how do I define a convex IP? Well, I take any convex function, and for now, I'm going to assume that it has a gradient f. And I'm also going to assume that my function has that the level sets are bounded. Okay, so this assumption, we make it explicitly. So if you're following along with the IPCO paper, I should say that we make this explicitly in some of our proofs, but it's not very clear sort of in the whole paper. And so this will be made more clear in the final version. And we want to thank the reviewers who noticed that we need to be more clear about this. But anyway, so we assume that the level sets are bounded. And so what we do, we're actually considering sort of the simplest convex IP, which is there's no additional constraints, just minimize f over this mixed integer lattice. Okay, and this problem has been studied in many for a long time. I mean, this this generalizes, say, the closest vector problem. And so even if you want to go into that direction and think about algorithms for solving that, I mean, this model would capture that. Okay. So our goal is to, again, to construct optimality certificates for this problem here. Okay. So how do lattice-free sets come into play as optimality certificates? Well, so what I've drawn here, suppose that, oh, there's supposed to be a line here. I wonder if I can, anyways. So suppose that I have my function f and I take a point x and I evaluate its gradient, and what this gradient will do is it will define a half space which is tangent to the level curves. Okay, and this is all by convexity. So if I have a point x and I take another point y where the function value is strictly less than f of x, then y has to live inside of this open half space defined by the gradient. Okay, this all follows from convexity. Okay, so suppose I have some candidate for my optimal solution x. Well, I mean, y might be something that has a function value less than x. Okay, but I can push this a little bit farther and say, suppose I have 2 points now, x and x bar. I have 2 candidates for my minimum. And if I want to find a better solution, then I have to look in the intersection of these half spaces. Okay. So I can be even more clever and choose, I mean, suppose I choose these 4 points, these red points, and suppose that if I create these gradient hyperplanes, I get this set here. Well, if I want a point y whose function value is less than all 4 of these, then it has to be in the interior of this set. So suppose I want to find an integer point y whose function value is less than all 4 of these. Well, I mean, this set, this red set, is lattice-free with respect to Z2. And so this lattice-free set certifies that one of these 4 points has to be my optimal solution. So with this in mind, this leads to a notion of a gradient polyhedron. So if I take a non-empty and finite set of lattice points, then the gradient polyhedron is just if I take these points and evaluate the gradients at all of these points, the resulting polyhedron is what I call the gradient polyhedron. And as we just discussed, if you can find these points x such that the gradient polyhedron is lattice-free, then one of the points in x has to be your optimal solution. Okay. So are there any questions on this? I mean, this is our main object for the talk. Okay. So let's see. So there has been some work on how these gradient polyhedra can be used to certify optimality, but to the best of my knowledge, most of this has been done from a theory, from an existential point of view. So there's this theorem, and I'll read it first and then talk about the references. But the theorem states that if you have a mixed integer point and it happens to be optimal for your problem, then what you can do is you can find this set x where your minimizer is in that set. The gradient polyhedron happens to be lattice-free, But also, I mean, and this is an important thing that we'll be using, that the number of points in your set is at most 2 to the n. Okay, and this is, I mean, for those of you who have seen lattice-free sets before, this value of 2 to the n is familiar. Okay. So the question that we wanted to tackle was, can we take this existential result and make it constructive? So can we actually build this set X that only has 2 to the n many points inside, such that it's lattice-free, and then of course this would give us a way of solving the convex minimization problem. Okay, so before I get to our results, I want to spend a little bit more time talking about what can we say about how to algorithmically construct these sets. Okay, so can we possibly construct these lattice-free sets such that this certification set X is not too big? And the simplest case is when n is equal to 0. Okay, so when n is equal to 0, there's no integer points, and our convex minimization problem is just a continuous convex minimization problem. Okay, so how can we solve this? Well, one of the more classic algorithms for solving this is gradient descent. So what I'm going to do now is try to describe gradient descent to you in the language of lattice-free sets. So suppose you make an initial guess, here I call it x star, at what the minimizer of your function is. Well, suppose this is the point, and here you can see the level curves in blue, and of course the gradient polyhedron, this big red thing, is not lattice-free. I mean, the lattice is now RD. And so what gradient descent does is it updates this x star to a new point, a new x star, which we chose from inside the gradient polyhedron. Okay. Well, now we have a new gradient polyhedron. It's still not lattice-free, and so what gradient descent does is it chooses another point inside of the set, and it keeps going until you're lattice-free. And something is wrong here, but what happens is that this is lattice-free if and only if the gradient, sorry, I'm drawing with my mouse now, this gradient is equal to 0. Okay, so this is the first order optimality condition that many of us know from convex optimization, and it turns out that this is just another way of saying that your set is lattice-free. And this is actually why we needed that alternative definition of interior, because at some point we might stumble across a point x star that satisfies this, and so we want it to be lattice-free. Okay. Okay. So based off of this gradient descent algorithm, I actually want to update my question, because gradient descent is very nice in the sense that you can start at any point you want, and it iteratively leads to new gradient polyhedra, and along the way, all of the polyhedra, so all of these points that we saw before, each of these sets is at most 2 to the n in cardinality. So I'm going to modify the question to ask that more generally. Okay, so can we iteratively construct these lattice-free sets, and along the way only carry 2 to the n many points with us? So we saw that we can do it when n is 0. But what about when n is 1? Well, this case is also simple in some sense. So suppose we have this function here, this, I don't know, I guess this is a quadratic function. And suppose I make a guess as to what my minimizers are. Well, I should say now n is 1, whoops, and 2 to the n is 2. So I'm allowed to have 2 points in my set. Suppose I choose these two. Well, the lattice or the gradient polyhedron is just this ray. And so all I'm going to do is kind of flip along the line. I already gave you the punchline. But in this one-dimensional case, you can just keep flipping along the line. And what this flipping does is it always keeps at most 2 points in our set. And at some point, you'll straddle the continuous minimizer. And at that point, one of these two is going to be the minimum of your function. Okay, so our theorem, or sort of our contribution, is that you can do something similar in 2 dimensions. So, I mean, in 1 dimension, as we just saw, we can sort of flip these points along the line. But now in 2 dimensions, you have enough freedom. I mean, you can't just flip in one direction. You have to, there's some decisions to be made. And so, so our theorem states, or it's read as follows. So if we start with any, I'm going to call it a unimodular set. So what is a unimodular set? Well, it's any set of integer points where the convex hull of the integer points is equal to the set itself. So it's really defined by some unimodular matrix plus an anchor point here. So if we start with any of these sets, we can generate a sequence of unimodular sets such that eventually we become lattice-free. And also, I mean, this third bullet point, it states that when we do our updates, we only use information from the gradients. Okay, so one nice thing about the sort of the classic gradient descent algorithm is that it's a very quick update. You only check the gradient and then you move in the opposite direction. And we wanted to try to imitate that with our algorithm. And what we're able to do is we can use this gradient information, and I think we have to use maybe 10 or 12 different gradient comparisons, but a constant number, and then this lets us update towards the next iteration. Okay. So, oh, and I guess I said this was when we have 2 variables, 2 integer variables, and all of my pictures have been when there's 0 continuous variables. This extends to sort of arbitrary d, but all of my pictures are when d is equal to 0 as well. Okay. Oh, sorry. I should say it extends to arbitrary d, but I'll come back to that because we need an additional assumption there. So how does the algorithm work? Well, I don't have time to go into all of the details, and they're not all in the IPCO paper. We didn't have enough space, but they will be in the final version. But the idea here is just to start with one of these unimodular sets and flip it to some new set. So just update our unimodular set to a new set. Okay, and as you can see with these pictures, what happens is we get this sequence of unimodular sets. Sometimes the shape of the set stays the same. Sometimes it gets perturbed, but this is the idea. Okay. So I think I have time. So what I'm going to do, whoops, sorry. Why is this not working? Okay. So what I'm going to do, I think this is best seen with sort of more of a visualization. So can everyone see this here? Okay, this is a nice little interface that Miriam made. So, okay, so what I see here is the 2-dimensional integer lattice. And my function f is going to be a quadratic function with this matrix A and this translation B, but just, oops. Just to give you sort of a visualization, let me start this over. So just to give you a visualization, this is what the level curve looks like of this quadratic function. This red point happens to be the continuous minimizer. And again, what we do is we start with any unimodular set. So here I've chosen this green square. Okay. The gradient polyhedra.
You have 5 minutes.
Okay, thanks. Yeah, I'm almost done. So the gradient polyhedron is this highlighted red region. And our flips lead to something like this. So the gradient, so this unimodular set kind of follows the gradients, and then at some point it will turn around and approach sort of the integer minimum, and at some point it terminates, and as you can see, this split that we end up with is lattice-free. Okay. Just a visualization of how all of this works. So yeah, so there's, I won't go into the details. There's 5 cases for how we define our flips, and it's dependent on sort of the structure of these unimodular sets and what the current gradient polyhedron looks like. To measure progress, we use 2 different metrics. One is we make sure that the minimum function value evaluated on our unimodular set, this always is non-increasing. And the second measure that we use, so these unimodular sets, as I said before, they're defined using a unimodular matrix U. So with the picture, what this means is that there's these 2 vectors, U1 and U2, and this actually defines a distance between integer points, not in my unimodular set, and the unimodular set itself. And this distance, it just takes an integer point, like this y bar, and it counts how many times I need to use my vectors, U1 and U2, to reach my, my unimodular set. Okay. I can talk more about this if someone's interested. But we have these 2, so we have these 2 measures of progress. One is this function value, and one is this more graphic measure. And it turns out that if our current choice does not contain a minimizer, then after 2 flips, one of these things has to decrease. Okay, and then this, along with our boundedness assumption of the level sets, eventually means that we will terminate. So I'll skip this. This is just a diagram of kind of how the convergence works. And just as a last comment, I'll say that there are some extensions that we have been digging into. So one of these extensions is that our flips, so if we have general convex functions f, then our flips will always find a minimum. So in the beginning, I assumed that all of the level sets were bounded. If you remove this assumption, then our flips will still find a minimum, although we can't certify that eventually we become lattice-free. And also so for running times, if we assume that our function is also Lipschitz continuous and strongly convex, then we can analyze our updates, and we see that in about this many steps. So what is this? We also need a bound sort of on how far or how big our integer optimal solution is. This assumption is often made when analyzing the running time of gradient descent. So linear in this distance, we can obtain a minimum value. Okay. This is not the best running time. I mean, there's other algorithms that have less dependence on these parameters, but just for our simple updates, we can show that you converge to a minimum in this time. So not a lattice-free set, but just a minimum. So I skipped over a lot of details, and there's lots of open questions in the future. Basically, any question you have is an open question, but I'd be happy to discuss. I'm very interested in this. But I'll just stop there and say thank you for listening.
Thank you so much, Joe. I have 2 questions for you at this point. I want to give the word to Kshite Set to begin with. Please unmute yourself.
Yeah, hi. So I just had a naive question. Can the problem of finding lattice-free sets be like, sorry, can SVP be reduced to finding lattice-free sets? Because intuitively it feels like if you find a short basis, like lattice-free sets would find a very short basis, right? Possibly the shortest.
I'm not sure off the top of my head. I mean, you're right. Your intuition is right that if you have the short basis, then this should be related to a lattice-free set. But what's nice about the closest lattice vector problem is that, I mean, it really does become it really is this convex minimization problem, as I stated. But I'd be happy to talk more about this afterwards. I would have to think about it a little bit.
Okay, thanks.
Okay, then I have Michele Conforti, please.
Hello.
Hello, good morning.
Very nice. So I didn't get the bottom line. Is this like a polynomial time algorithm? Well, it all depends what polynomial means in the sense how the function is given, what is the starting point.
Right.
But is this like a good algorithm for convex integer minimization in the plane? Or in
No, I mean,
no.
no. The bottom line is there's better things to do. I guess I wasn't very clear about this, but the point of this algorithm was really twofold. One is to try to build these lattice-free sets and see perhaps in higher dimensions we can use some of these ideas to come up with this new geometric algorithm for solving this minimization problem. But the other motivation was to come up with an algorithm that imitates gradient descent. I mean, because gradient descent is extremely effective in practice, even if the running times in theory are not the best. So what we wanted to do is to find some way of taking these lattice-free sets and quickly updating them to take these gradient polyhedra, which are not lattice-free, and quickly update them without having to solve IPs or something like this. So this is more of sort of a conceptual framework for an extension of gradient descent to the integer setting.
Okay, I have one more question,
Okay.
so I
will
don't
ask
know.
offline.
So Manarli, you can ask your question. Manarli Sharma, you had a question?
Yeah, sorry, I wasn't able to unmute. So hi, thanks for the nice talk. So I see a lot of connections of this work with derivative-free algorithms in some sense. Of course, you are using the very extensively here, but have you thought of any connections for solving DFO problems, derivative problems on this?
Sorry, the audio cut out briefly. I wasn't able to understand the question. Could you please repeat the question?
Yeah, I'm audible now.
Oh,
Am I audible? Hello.
hi. Sorry, I mean, I can hear words, but it's very choppy.
There's a written version of the question, I think. How can this algorithm be adapted for derivative-free problems?
So right now the algorithm, I mean, I was talking about these gradients the entire time. It can be adapted, it can be generalized to subgradients. We just need some, yeah, we need some way of creating a direction to move into. And I haven't thought about if this is possible if you sort of don't use gradients in any manner. One thing is that you can, I mentioned that you can extend this to mixed integer problems. And this is kind of ongoing work that we briefly introduce in the full version. But what you can do if you have, I think it's the assumption of strong convexity. What you can do is you can use approximate gradient information. So you don't actually need the true gradient. You can use some approximation of it. And this is still enough to guarantee that eventually your set becomes lattice-free.
Okay, thank you, Joe. I think in the interest of time, we have to cut. So I invite everyone to unmute themselves to give an applause. And this applause is also for you, Dabin, because I forgot to ask people to unmute when they were applauding you. So thanks a lot, Joe.